Hi, here's a really interesting problem taken from Oxford University's BMX maths competition. We have a group of 2n+1 individuals follows the property. For any group of n persons, there exists one person among the remaining n+1 such that he knows each of the n individuals. Prove that there exists a person who knows all the other 2n individuals. And note that if A knows B, that's the same thing as B knowing A. So it's a two-way relationship. Now, I labeled this problem the BNOC problem because BNOC stands for big name on campus. So someone at a university who seems to know everyone, and this is what this problem reminded me of. So we have an odd number of people with the property that if you take any group of n people, the n+1 people who are left over, there's someone in those n+1 who knows who knows all of the n selected people, and with that information, we want to prove that there is someone who knows all the other 2n individuals. Anyway, if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to dive straight into a solution. So it's very easy to convince yourself that we're going to need lots of graph theory for this solution. Turns out we don't need any graph theory whatsoever. What I'm going to do is start by defining a friendly group to just be a collection of people who all know each other. So if there are 5 people, all of whom knew each other, we'd call that group of 5 people a friendly group. What we're going to do is call all of our 2n+1 individuals, we'll call X, or we'll call that the set X. So X contains the 2n+1 people. And what I'm going to do is take a subset of X, and I'll call that Y, and Y is going to be a friendly group. So Y is going to be some people out of the 2n+1, all of whom know each other. And in particular, I'm going to choose Y to be as big as possible. So Y is friendly, and Y is as big as possible. So it's the biggest possible friendly group subset of X. Okay, what do I know about Y then? Well, Y has to be at least size n+1. Why is that? Well, if it had size less than or equal to n, well, I could apply this property up here. I could choose someone among the remaining n+1 people who knew everyone in Y. But if that person then knew everyone in Y, I could call that person, let me call that person X. If I looked at this set here, this would be a friendly group, and it's clearly bigger than Y. But that contradicts the fact that Y is as big as possible. And so therefore Y must have size at least n+1. Okay, cool. So Y has size at least n+1. So if I look at Z, which I'll call X without Y, so basically all the people who are left over, this guy here must have size at most n. Cool. Now what I can do is say with Z is, again, apply the property on Z. Z is a group of people of size at most n, and so therefore out of the remaining n+1 people, there is someone who knows everybody in Z. So out of the people there's someone who isn't in Z who knows everyone in Z. But if there's someone who's not in Z, they must therefore be in Y. And so what I've got is there's this person, let's call them Y in Y, and Y knows everyone in Z, but because Y is in Y, Y also knows everyone in Y. And Y and Z, if I put them together, I get X. And so therefore this person Y knows everyone in the set. They know all X, all the people in X here. And that solves our problem. This person Y is the BNOC. I hope this solution has made sense. It's a pretty cool problem, and it's got quite a neat solution here. I hope you have enjoyed this video. Thank you for watching. I'll catch you in the next one. Have a great day.